Welcome to video lecture on dynamics of machinery. In the today's lecture, we'll discuss about numericals on free undamped single degree of freedom system. So let us start the numerical on this topic. Write the equation of motion of the system as shown in figure and find its natural frequency. Now, if you look towards this system consists of mass as well as pulley. If such type of the systems are there, then we can solve this problems by using energy method easily. Okay, so first of all, if you look towards this case, okay, in this case the combined motion is there. Okay, so if we just concentrate on this mass, if I pull this mass in downward direction, at the same time the mass is attached at the end of this one rope or string. Okay, that is wrapped on the surface of this pulley, and another end of this string or rope is connected with this spring. Okay, so when I pull this mass in a downward direction, the pulley get or rotates or circular motion possessed by this pulley. Means when I pull this one in downward direction, okay, this is the thing, but the linear motion possessed by that mass. At the same time, this will rotate, okay, in some angle, rotates, okay, with some angular motion. Okay, so we can solve this problem step by step, solving by energy method. For that, we know energy method. So total energy consists of potential energy as well as kinetic energy. Okay, so as per our discussion, this is a case of combined motion, that is translation motion due to mass m, small m, okay, and torsional motion due to pulley of mass, say here capital M, and hence energy for both should be considered. So what's about the kinetic energy possessed by this system? So if you concentrate on this small mass, okay, so before that, let us say what's about the kinetic energy, total kinetic energy of the system. It consists of, if you look towards this small mass, okay, whatever the kinetic energy possessed by this small mass because of the translatory motion, or you can just say the linear motion possessed by this mass, as well as kinetic energy possessed by this one pulley because of torsional or rotational motion. So what's about the kinetic energy? If I consider this one translatory motion, just by the small mass, okay, we know the kinetic energy is nothing but 1/2 mass into its velocity square. If you look towards this one, this mass, if I pull this mass in downward direction, so the displacement will occur because of this distance x. Okay, so what's about the velocity of the same? X single dot indicate its velocity, so we can get the kinetic energy possessed by this mass because of its translatory motion or linear motion is nothing but 1/2 mass into its velocity square. Okay, so if I draw the displacement diagram or free body diagram for this system, then the system will looks like this. So here is the pulley. Okay, in this way. Okay, so if you just consider the displacement of the mass takes place from its original position to next position, like this one. Mass with us here m, same mass will remains as it is. Just say this is nothing but the B position, this indicates the B dash position. Okay, so if you look to us here, so whatever the displacement of this pulley takes place by angle, just say theta angle. Okay, so I'll just say here A point with us, A dash point is here. Okay, so at the same time, if you look towards this spring, the spring also get expanded like this one. Now, by considering these fundamental things, okay, so whatever the angle theta with us here and linear displacement, I'll just show that linear displacement by distance x. Okay, so the mass moves by, you just consider the mass moves by shape. The mass moves by small x, this mass. Okay, and if there is no slippage, then the pulley rotates by angle theta, such that if you look towards this one, if I pull this mass in downward direction, so displacement occur by distance x. Okay, at the same time the pulley rotate by angle theta. Our aim is to get the relation between this theta and this x. Okay, so for the smaller angle I can just say uh, whatever this linear displacement, that is b dash equals to, what's about this one, a dash is nothing but the arc. Okay, arc a dash. So easily can write this relation for the smaller angle. This arc a dash is nothing but whatever the radius of this one, radius of this pulley with a small r and angle with us here theta. So you can easily write here x equals to r theta. Okay, so at initial stage already we get the kinetic energy possessed by this mass because of his translatory motion or linear motion. Now our next target is to get the kinetic energy possessed by this pulley because of the torsional motion. Okay, torsional or rotational motion possessed by this pulley. Okay, so what's about the kinetic energy by torsional motion of this pulley? You can get this way 1/2 mass we can get in terms of mass moment of inertia of this disk, that is I, and its velocity you can get in terms of theta. Okay, so theta single dot indicates its velocity. Since here I equals to mr square divided by, so mass is given here, capital M mass given for this pulley, and mass moment of inertia, if you just consider this is nothing but the x-axis. Okay, so the mass moment of inertia along x-axis is nothing but the mr square by 2. So already this thing studied by you in strength of material. Okay, so simply as far as concerned with our case, remember this formula, this one, and just move towards next step. So kinetic energy during the torsional motion is nothing but here 1/2. So I with us capital M into small r square by 2, like this one. Okay, Now into theta single dot square. Try to simplify this. Here we can get 1 by 4, 2 multiplied by 2, 4 m r square remains as it is, theta single dot square remains as it is. Now we can get information regarding kinetic energy during the translatory motion and kinetic energy during rotational motion. Okay, the two relations with us. Now by getting these two values, now next target is to get the value for the potential energy. Okay, for that I'll just erase some portion from this side. So what's about the potential energy? We know the potential energy is possessed by spring. Okay, so what's about the potential energy or strain energy by the spring toward in spring? Okay, the displacement here, the displacement occur by x means the same displacement for this spring also comes. So 1/2, as per our previous discussion, we know 1/2 k into x square in this way. So what's about the total energy, that is U? U is nothing but, so already here relation is written, potential energy plus kinetic energy, that will remains constant. So this kinetic energy is nothing but addition of this one energy possessed by this mass during the translatory motion and during the torsional motion. So write it here clearly. U equals to potential energy with us 1/2 k into x square plus kinetic energy is nothing but here total kinetic energy. Yeah, that will remains constant. Okay, so what's about the total energy? Total energy, you have to add this with this one. Okay, so 1/2 m x single dot square plus next 1 by 4 capital M r square theta square. Okay, if you look towards this one, x single dot is here and theta single dot is here, and just now my target is to get the relation for the frequency. Okay, so we can easily differentiate this with respect to timing t. Before that, we know the relation, since this relation with us x equals to r theta. Okay, x equals to r theta, this relation already with us. Okay, so if x equals to r theta, what's about the x single dot? You have to just differentiate this one with respect to time t. We can get x single dot equals to r into theta single dot. Okay, so my target is to get this equation in one variable only. Okay, so differentiating, before that differentiation, just replace this x by r theta and x single dot by r into theta single dot. Okay, so from this equation you can get u equals to 1/2 k will remains as it is. You have to replace this k term by r into theta term. So r square into theta square term will come plus 1/2 mass into x single dot means r square single, this one theta single dot square. Okay, this is about the x single dot square. Next one, 1/2 capital M into r square, theta will remain as it is, theta single dot square. Now we can easily differentiate this equation with respect to time t. Differentiating with respect to time t and using principle of energy. Okay, so differentiate this one. Du by dt equals to 1/2. You have to just differentiate this equation with respect to time t. So these terms are constant, so keep this constant term as it is. Okay, so 2 will come here. I'll just write this 2 here. 2 theta, derivative of this one theta, again derivative of theta will remain, so theta single dot will come here, plus next one, this term is constant, so write this term as it is, 1/2 mass into r square. Again derivative of this term is nothing but 2 will come here, so theta single dot, theta double dot will come. So in the next part you have to take the derivative of this one with respect to time t. This term is constant, so 2 divided by 2 m r square. So what's about this one? Theta single dot, theta double dot equate with the 0. Okay, because total energy remains constant. Okay, this is the principle of energy. Okay, so this term get cancelled, this term get cancelled, this one get cancelled. So if you look towards all the terms, the theta single dot is common. So we can write this relation like this one, k r square theta plus next one m r square. Here actually 1/4, not 1/2 here. So here the 2 will remain. So in the next part, m r square theta double dot plus next one m capital M into r square divided by 2 into theta double dot. Okay, so you have to take this one theta single dot as common and equate with the 0. Since the velocity in the system never becomes 0, so theta is not equals to 0 in this case. So what's about the next one? If the theta single dot is not equals to 0, means second bracket must be equals to 0. So what's about this one? So next step will come like this. Theta, sorry, k, and just take this r square term common from all the terms. So k into theta plus m r square. Instead of that r square, I'll just simply write here theta double dot m into theta double dot plus capital M into theta double dot by 2. Okay, like this. I'll just take r square term as common. Okay, and already as per our discussion here, theta single dot is not equals to 0, means this bracket must be equals to 0. Since here in this case r is not also equals to 0, means here we can simply equate this bracket by taking r as common. We can equate this bracket with the 0. Now write this equation in a such way that we can compare this equation with the SHM equation. For that I'll just make few changes in this equation like this, or a rearrangement of this equation like this. Take this theta double dot as common and write the mass terms inside of the bracket plus this one k into theta equate with the 0. Now we can easily compare this equation with the SHM equation. Equating with simple harmonic motion equation. So what's about this one? We know the simple harmonic equation for the motion is nothing but theta double dot into omega n square into theta equals 0. So if we compare this equation, before that you need to again modify equation number. Next one is just equation number 3 is here. Modify equation number 3 in a such a way that we can compare this equation with this equation. So K divided by capital M by small m by capital M by 2. K will remain as it is. Just divide this term, okay, to this term, write this theta here and equate with the 0. So easily we can compare this equation 4 with equation number 5. So what do we get here? Omega n equals to, what do we get here? Omega n equals to square root of K by M, means here K with us in this way, and M we can get like this. Just simplify this term like this one. 2 multiplied by M, 2n plus n. So the 2 will come here like this. You can get this relation in terms of radian per second, okay, and in this way you can get the relation in terms of hertz. 2k divided by 2m plus capital M in terms of hertz. Like this. So next problem, find the frequency of oscillation for the roller if it rolls without slipping for the system as shown in figure. If the roller radius was doubled, keeping the mass same by using a lighter material, what would be the new frequency? The system is given like this one. So it consists of one roller and a spring, okay. So spring is attached at the center of this roller, okay, and to the another end the spring is connected at the fixed support, okay. So whenever I pull this roller, okay, the roller will rolls on this flat surface in this way, and the spring get expanded. So stiffness of the spring is also given, mass for this roller is given, radius for this roller is given, okay. So to solve this problem, you can easily get the solution by using the energy method, because it consists of this one mass as well as spring, and this mass possesses the two different motions. One because of its linear motion or translatory motion on the flat surface, and second one because of its rotational motion or torsional motion about its own axis, okay. Now if you look towards this one, so kinetic energy possessed by this roller because of the translatory motion and because of the torsional motion. So another thing here available with us, when this roller moves by distance x. Now just focus here. I'll just say this point is nothing but here, initially a point is here, the moment of this center of the roller takes place by distance x, okay. At the same time this will rotate by a certain angle, that is angle theta. So my aim is to get the relation between this linear motion as well as this one angular motion. So what we get here, we can get in terms of this one x equals to r theta. So radius for this one, a roller with us r, and simply we can get the relation for this x single dot like this one, x theta single dot in this way, x single dot divided by radius r, okay. So what's about the kinetic energy here? Simply you can get the kinetic energy when the roller possesses translatory motion. So what's about the kinetic energy? 1/2 mass multiplied by its velocity square. So during the linear motion or translatory motion, you can just consider the linear displacement and linear velocity. So what's about the next one? During this torsional motion, kinetic energy possessed by this mass is nothing but 1/2 the mass moment of inertia of this roller should be considered. So 1/2 multiplied by I into its angular velocity square, like this. So what's about the potential energy? So potential energy possessed by this spring is nothing but 1/2 k into x square, like this. So what's about the total energy? So total energy is nothing but kinetic energy plus potential energy. So kinetic energy already with us from equation number 1, from equation number 2, potential energy with us. So right here kinetic energy, I'll just move the suffix for this one as total. So total kinetic energy is nothing but kinetic energy during translatory motion as well as torsional motions. 1/2 mass multiplied by x single dot square plus 1/2 I into theta single dot square this way plus 1/2 k into x square. In this you can get the total energy. Okay. So in case of disc or a roller, we know case of disc or a roller, we know I is nothing but m 1/2 into m multiplied by its radius square. Okay. So my target is to bring this equation into one variable. So in this case, we know the relation for this theta single dot. Already relation for this theta single dot with us. So modify equation number 3. So from equation number 3, what do we get? U equals to 1/2 mass into x single dot square plus 1/2. So I should be replaced by this term 1/2 mass multiplied by r square. This I should be replaced by this one. And theta, this theta value with us here, theta single dot is nothing but x single dot divided by this r whole bracket square plus 1/2 k into x square must be equals to constant as per energy method. Now differentiate this equation with respect to time t. Differentiating with respect to time t, what do we get here? Du by dt equals to 1/2 m will remain as it is. What's about the derivative of this term? The 2 will come here, x single dot x double dot will come here. So next one, simplify this 1 by 2, 1 by 2, this term is constant term, this will remain as it is, and this 2 term, okay, goes here. So 2 by 2 into 1/2 m r square. So derivative of this term here, the r square constant, so write this r square in this way, 1 upon r square. So what's about here? The 2 term already we are written here, x single dot into x double dot, okay, will come here. So plus next one, for this case the 2 will come here, okay, 2 by 2 into k. What's about the derivative of x? So x into x single dot equate with the 0. Okay. Now what's about the next step? Just continue that next step this side. Now here the 2 get cancelled, 2 get cancelled, this 2 get cancelled, this r square also get cancelled. Now from all the terms, first of all take this x single dot as common. So I'll write this in this way, mx double dot plus next one, 1/2 will remain as it is. What's about the next one? This m, and here r square already get cancelled. So what's about next step? In the next step we can get m by 2 into x double dot. Okay, only x single dot, already our plan is to take that x single dot as common, so I'll not write here that x single dot. Okay, so the next step we can get k into x, take this x single dot as common and equate with the 0. So as per our previous discussion, this x single dot should not be equals to 0. Okay, so what's about the next one? The equation will be modified like this. So this small m, this also small m, so 1 plus 1/2 means 3 by 2 into x single dot will come here. Okay, 3 by 2 into m into x single dot. Okay, this will come like this one. So k into x, okay, this term, and equate this with the 0. Here just clearly write x is not x single dot is not equals to 0, means the second bracket, this must be equal to 0. Okay, so what's about the next one? Now rewrite this equation in a such way that we can compare this equation with the SHM equation. So 3 by 2 m goes in denominator into x equate with the 0. We know SHM equation. We know SHM equation. So what's about that equation? X single x double dot plus omega n square into x equals to 0. Equate this equation. Equation number, next one, equation number 4 is here, equation number 5 is here. Just compare equation number 4 and equation number 5 and see what we get. So we can get omega n square equals to, what do we get here? Root of k by m, this term, k by m, 2 will goes in numerator, so 2k by 3m. In this way that term will occur. So already the values for this k and m is given in the problem, so the square will not appear. So omega n equals to square root of 2k divided by 3m, like this. So what's about the value of k? K is given 9810 Newton per meter, and the next one, the mass for this roller is also given. So what's about the mass? 3 multiplied by mass is given 6 kilogram. If you simplify this, we can get the omega n equals to 33.015 radian per second. Now see what's about our next target. Our first aim is to find out the frequency for the oscillation, and the next one, if the roller radius was doubled, keeping the mass same by using a lighter material, what would be the new frequency? This is the question asked. So for that, if you look towards this relation obtained for the frequency carefully, here no any radius term available with us. Only this omega depends upon k and m. So answer for the second question is there will be no change in the frequency if you do this with the ruler or with the system. Here just clearly mention keeping the same mass and radius doubled, the frequency will remain same. The answer for this one will remains as it is 33.015 radian per second. So let us start next problem. Find the frequency of the system shown in the figure. So system consists of one mass is attached at the inner step of this pulley. Okay, so on the outer periphery of this pulley. Okay, so what's about this one? The spring is connected towards one side, and another end of the spring is connected with the fixed end, and here with the help of this string towards the inner side of that pulley, the mass is attached. So whenever this mass is pulled in downward direction during this displaced position, because that the radius for this small step with a small r and radius for this bigger circle, okay, in short is given capital R. So whenever the displacement takes place, linear displacement takes place by distance, this one x, the angular displacement takes place by this one theta. Okay, so by using energy method, we can get first of all the kinetic energy. In the next step, we can get the information regarding the potential energy, as the system consists of the spring as well as here the two masses. First one here in terms of this one mass attached that actually moves in downward direction or in translatory motion at the same time this or rotates. Okay, so by energy method, first of all get the kinetic energy. So total kinetic energy includes the kinetic energy possessed by this mass because of its linear or translatory motion. So what's about this one? One half mass with a small m. So what's about the velocity? As the displacement with us in terms of x. So velocity we can get x single dot square plus one half. So what's about the mass moment of inertia of this whole pulley? So I with us. So what's about this one? Theta single dot indicate the velocity, torsional velocity or rotational. Here we can just say the angular velocity of this pulley with us theta single dot. Whole square of this one will come. So where this x is nothing but here linear displacement. So for this small displacement you can just say angle theta with us. So you can easily get the relation between this x and theta. So radius for the small portion with us smaller, so you can easily get x equals to r theta like this. So theta you can get in this way, x divided by r. So angle theta, this theta is the angle turned by pulley due to this rotation at the periphery of the spring. This one periphery of the spring get deflected by delta. So whatever the displacement of this spring takes place, so if you look towards here, delta is nothing but here capital R into theta. So capital R is nothing but this radius. So this displacement here, linear displacement in terms of delta, and here r is nothing but the radius of this portion and theta already with us. So for this deflection of the spring we can get the relation delta equals to capital R into theta. So what's about this theta? So if you look towards this theta, theta is nothing but delta divided by r. In this we can get the relation. So initially or in the previous step already the value for the theta with us x divided by r. Simply equate this term with the previous one, x divided by r. So what do we get here? Delta. So delta in terms of this x divided by r, this we can get it. Delta equals to capital R will come here, capital R into x will remain as it is and r will remain as it is. So what's about the potential energy? So potential energy, by considering this displacement delta, we can get 1 half k into delta square. So what's about the potential energy? 1 half k into k will remain as it is. You have to replace this delta term by capital R into x divided by r. So capital R divided by this one r into x, whole bracket square will come here, okay, because delta square with us right now here. So squaring this one r square x square and this one r square, get the next step. Okay, for the potential energy you can get this relation. So what's about the total energy? Total energy is the thing but addition of kinetic energy plus this is the potential energy with us. So what's about the kinetic energy? Kinetic energy already we get from this relation, right? Total kinetic energy. So write this term as it is, and in the next step potential energy with us, write this here. So in the next step you have to replace this theta term by this one, this relation. So here theta is nothing but here displacement, angular displacement. So here we want the angular velocity. So angular velocity is nothing but the derivative of this term. So here we can get theta single dot is nothing but x single dot divided by r. So you have to replace this theta single dot by this one theta x single dot by r. Okay. So square of this one here. So the square for this term also come here. So in the next step write this term as it is. Now by using the energy principle. So what's about the energy principle? So as per as consider the energy principle, you have to differentiate this equation with respect to time t. For that, if we take the derivative of this term, okay, the 2 will come here. So 2 by 2 into m into x single dot will remain as it is, x double dot plus the next step 1 half, okay, 1 half term as it is, I term as it is, r square term as it is. So what's about the derivative of this one? X single dot. Again derivative of x single dot is nothing but x double dot plus next one. This term is constant term, so write this term as it is, and the remaining one is nothing but here x. Derivative of this x is nothing but 2 will occurs here. 2 x derivative of x is nothing but here x and x single dot. Okay, like this, and equate with the 0 because the derivative of constant is nothing but the 0. Now focus on this equation carefully. So 2 get cancelled here, 2 get cancelled. The next step, this one 2 get cancelled. So whatever the part remains here. Okay, so here I'll write that part inside of the bracket like this one. M remains here plus I into r square. Just take this x double dot as common plus here. What's about the next one? K into r square divided by r square into x right here. Take this x single dot as common and equate with the 0. Since this x single dot is not equals to 0, this bracket must be equals to 0. Okay, so equate this bracket equals to 0 and just rearrange some terms. So r square multiplied by this m will come here, plus I will remain as it is. So r square. So if I multiply by this one r square here, this r square term get cancelled. Whatever the part remains here, k into r square into x equal to 0. Simply just equate this equation with the SHM equation. So directly we can get here omega n equals to k r square. Here x double dot plus k r square into x. This term with us. This term goes in denominator. Okay. If I compare this term with the SHM equation, what do we get? Omega n equals to square root of k r square divided by this one, this bracket, I plus m into r square in terms of radian per second.